Hi everyone, today we are going to start a new chapter which is called electrostatic potential and capacitance. First we will discuss about electrostatic potential. Now in class 11 you have already studied about potential energy, elastic potential energy, gravitational potential energy and also gravitational potential. This is somewhat similar to gravitational potential. Now to understand it, let us consider a charge plus cube is situated at this point. So because of this charge, an electric field will be created surrounding it. Now let us introduce a test charge Q. Suppose this is at the point R. We want to take it to a point P. Now because of this electric field, suppose both the charges are positive. Okay. So there will be a repulsive force on it. So if we want to take this charge from here to here, we have to do external work done. And for that we have to apply external force. Suppose we apply exactly the same amount of force which is experienced by this charge due to the electric field. So let's say F external equals to Fe in magnitude. So if you want to displace by a very small distance dr, the required work done will be Fxt dot dr. Now if you take vector notation, obviously F external and F electric field will be opposite to each other. So this will be the work done by the external force. Now if you want to take this charge from R to P, the total work done will be integration R F external dot dr. Now since we have done an external work done, the same amount of energy will be stored in this charge. Now this work done is against electric force, so there will be a gain in electrical potential energy of this charge. So we can write the change in potential energy or electrical potential energy as UP minus UR equals to W, the same amount of work done. Now here one thing we need to remember, that just like gravitational force, this electric force is also conservative force. So this work done is actually independent of path. Okay. Now if you want to calculate the potential energy, exact potential energy of this point P, we have to take such a point so that the UR becomes 0. So in that case, if we bring the charge from a point where the potential energy is 0 to this point P, so the difference will be UP. So in that way we will get the exact potential energy at that point. Now it is also very convenient to take that point at infinity. So we consider at infinity the potential energy equals to 0. So if we bring a charge from infinity to P, we will get the potential energy of the charge small q at point P. You can write here, suppose W infinity T to P equals to U. We can say potential energy or electrical potential energy of a charge at any point is the work done by the external force in bringing the charge from infinity to that point. Now this work done is definitely proportional to Q, since the electric force that is experiences is QE. So it is not independent of Q. So this work done does not give any characteristics of that electric field, since it depends on charge. So if you take a unit positive charge, in that case the work done gives characteristics of that electric field, and that is called electric potential or electrostatic potential, and we denote it as V. So you can write V equals to W infinity to P by the charge, or simply W by Q. Now this V is independent of Q, since it was proportional to Q and we divide it by Q. So it gives a characteristics of that electric field. So you can write work done by an external force in bringing a unit positive charge from infinity to a certain point is known as the electrostatic potential at that point. The unit of electrostatic potential is, from here you can write joule per coulomb, or also it is known as volt. Now try to find out its dimension on your own. Okay. Now let us find out potential due to a point charge. The expression of potential due to a point charge. Consider a point charge here, Q. We want to find out electrostatic potential due to this charge at a distance r from it. So what we have to do, we have to find out the work done in bringing a positive unit charge from infinity to this point. So that will be the electrostatic potential at this point. Now suppose at any instant the charge is at a distance r prime and center point is p prime. So the electric field at p prime due to charge q is equals to q by 4 pi epsilon naught r prime square, and it is directed along this direction. Now suppose against this electric field we move this charge from here to here by very small distance dr prime. So the direction of dr vector is along this. So you can see the electric field vector and this displacement vector are opposite to each other. So in moving the charge by small distance dr prime, the required work done will be dw equals to E dot dr prime. Now since E and dr vector are opposite to each other, we can write this is minus E dr prime. Just putting the values of E, we can get q by 4 pi epsilon naught dr prime by r prime square. Now similarly, we can find the total work done in bringing this charge from infinity to this point will be W equals to integration dw from infinity to r. Now we have to calculate this value. Just put the values minus infinity to r q by 4 pi epsilon naught dr prime by r prime square, and this one is constant. So just take out of the integration infinity to r dr prime by r prime square. By using formula you can write minus 1 by r prime, the limit will be infinity to r. So this minus and this minus will cancel each other by 4 pi epsilon naught, and we just put the limits here. First 1 by r in place of r prime, then 1 by infinity. 1 by infinity is 0, so we can write q by 4 pi epsilon naught. So this is the work done, and this work done, since the charge is unit positive, so this will be the electrostatic potential at this point because of the charge q. So this is our required formula. Now you can see the electric field actually varies as E proportional to 1 by r square, whereas the electrostatic potential varies as 1 by r. So potential actually decreases less rapidly compared to electrostatic field intensity. So if we draw them with distance E or V, we will see E is very rapid, whereas V is less rapid. This is E, this one is V. Let us find out potential due to an electric dipole. Consider an electric dipole q1 minus q charges and they are separated by distance 2a. We have to find potential at O. Now one thing we have to remember that the electrostatic potential is work done per unit charge. So it is a scalar quantity, right? So we will just add them like simple algebra. So suppose the distance of O from charge plus Q is R1 and that same from minus Q is say R2, and say this angle is theta. So the potential at O due to Q is V1 equals to 1 by 4 pi epsilon naught Q by R1, and the same for charge minus Q is equals to 1 by 4 pi epsilon naught. So this is minus Q by R2. We will just take the sign of the charge. So the total potential at O will be P equals to P1 plus V2. So this is 1 by 4 pi epsilon naught Q by R1 minus 1 by 4 pi epsilon naught Q by R2. Just taking common, Q by 4 pi epsilon naught 1 by R1 minus 1 by R2. Now we have to find the values of R1 and R2 in terms of R and A, right? For that, let us draw a perpendicular here. So if this is A, this part will be A cos theta and this one will be A sin theta. So in this right angle triangle, if we apply Pythagoras theorem, you can write R1 square equals to, now this one total is R, this one is A cos theta. So this one will be R minus A cos theta and this one is A sin theta. So R1 square equals to R minus A cos theta whole square plus A sin theta whole square. Just simplified, R square plus A square cos square theta minus 2AR cos theta plus A square sin square theta. Now these two terms will give you A square, since cos square theta plus sin square theta equals to 1. So you can write R square plus A square minus 2AR cos theta, which is R1 square equals to. Now if R is much greater than A, for that condition, for greater than A, we can write R1 square equals to, just take R square as common, this is 1 plus A square by R square minus 2A cos theta by R. So this term will be very small, so we actually can neglect it. So neglecting, we get R square 1 plus 2A cos, sorry, this is minus 2A cos theta by R. So R1 will be R1 minus 2A cos theta by R to the power half, or 1 by R1 will be 1 by R 1 minus 2A cos theta by R to the power minus half. So 1 by R1 equals to 1 by R 1 minus 2A cos theta by R to the power minus half. If we expand by binomially and we neglect the higher order terms, since R is very greater and it is, so we can write 1 minus, this one comes here, minus half into 2A cos theta by R. There will be more terms but we will neglect it because R is very greater. So we get 1 by R, this 2 will cancel, minus plus, so 1 plus A by R cos theta. So this is 1 by R. Now in similar way, we can get 1 by R2 equals to 1 by R 1 minus A by R cos theta. Now we'll put these two values in this equation. So we'll get V equals Q by 4 pi epsilon naught. 1 by R will come out as common. 1 by R1 equals to 1 plus A by R cos theta minus 1 by R2, which is equals to minus 1 plus A by R cos theta. 1 cancel. So we get finally Q by 4 pi epsilon naught 2A cos theta by R square. Again, you know, Q into 2A is actually the dipole moment, so you can write P cos theta by 4 pi epsilon naught R square. Now if you take unit vector along R, along is R cap, so we can write here that P dot R cap will be P cos theta. So we can write potential as P dot R cap divided by 4 pi epsilon naught R square. So this is the value of electrostatic potential due to an electric dipole at any point. Now here you have to remember that the whole derivation is on an approximation that the distance of the point is much greater than the size of the dipole. Also you can see here the potential actually decreases as proportional to 1 by R square. Now let us consider two cases. If the point we considered here is say on the axis here or here, so if the point is here, this line will be here, so the angle will be 0. If the point is here, the total angle will be 180 degree, right? So for those two cases, say theta equals to 0, that is an axial point. In that case, potential will be, just put cos theta equals to 0. So P by 4 pi epsilon naught R square. If it is 180, then there will be minus sign. Case 2, theta equals to 90 degree. 90 degree means the point will be on equatorial plane. So if we put theta equals to 90, you know cos 90 equals to 0, so the value of V will be 0. So on equatorial plane, on any point, the potential due to an electric dipole is 0. So this is it for today. Tomorrow we will study about potential due to system of charges.